Okay, so last time we almost concluded our survey of general stuff about conformal field theories. So today we will conclude the general remarks. Then we'll come back to CFT several times throughout this course. But as far as this very general big picture goes, today we will be done with it. And the last thing we learned last time was that since we know how to fuse two operators into one, we can apply it several times and get any correlation function as soon as we know the CFT data, which are the structure constants and the dimensions of operators. And in particular, if we have 4 points, for example, we can write that a 4-point correlation function is a sum over all primary operators OK. Then there is a probability, if you want, of creating operator OK from operator 1, 2, and the probability of annihilating operator OK into operators 3, 4. So these are some dynamical constants, creation and annihilation, that depend on the theory. Different theories will have different C1, 2K. And then, apart from this structure constants, then there is the propagation of the operator and all its descendants, because in a CFT, whenever you have a primary, you get all the descendants for free that are just derivatives of the primary. And then this object is called a conformal block. It's totally fixed by conformal symmetry like we saw. And here is the expression in D equals 4. So what is this expression? Well, we found it by applying the OPE and comparing the OPE with the 3-point function. So the way we would do it, actually, if we did it many terms, we would be comparing what we would be getting with a small z and z bar expression of this or what I wrote here. But this is the full resummation. That will be just a question of working hard to work out all those b, mu1, blah, blah, to mu(n). And if you work hard, you will find this result. So these are some hypergeometric functions. And z and z bar, remember, they are just a way of parametrizing the two independent cross ratios. Here is one cross ratio. Here is another one. And let's look at it. If I put the points at 0, 1, infinity, and the point 2, if I put it at some random location in the plane, at some x and y coordinates, then let's see what this cross ratio would be. You see that anything that involves point 4 disappears, because point 4 is at infinity, right? So this distance, it's infinity over infinity, it's 1, right? This over this is just 1. So I only care about these two. It's correct. It's not a joke. It's a polynomial. It's not like some fancy infinity. So here it's really correct. Okay. So now x1, 2 over x1, 3. x1, 3 is 1, right? Because 1 is at 0, 1 is at 1. So all this cross ratio here in this choice of points is just this distance, x1, 2 squared. And x1, 2 squared is this distance, so it's z times z bar. That's what I wrote there. What about this one here? Again, wherever 4 appears, this guy and this ratio is 1. This one is 1. And then I only care about x2, 3. And x2, 3 is the distance from 1. So it's 1 minus z times 1 minus z bar. So z and z bar are a clever way of parametrizing these cross ratios, and it's a particular nice one because then the block takes a very nice form. Now, then this gives us a decomposition of this conformal block. This is the block in D equals 4. And one thing we can do now is impose that the CFT is given by this set of CFT data, the structure constants and the anomalous dimensions, but not everything goes. It's not like I can give you give me any table of numbers. Right? If you give me a random table of numbers and say, here is your CFT, here's a list of deltas that I took from the yellow pages, and that's it. So take this list of numbers. It will fail miserably because immediately it will not be consistent. So one of the consistency conditions that you need to have is associativity of this OPE algebra that tells you that you can do the OPE first of 1, 2, or first of 2, 3, or first of 3, 4. And this associativity of this algebra, that is the algebra of OPE, is very constraining. Like associativity of algebra always is, right? That's how we label algebras and how we deal with group theory. And in particular, we have this infinite set of equations for infinite set of variables that tell you that if I OPE decompose in one channel, I must get the same as in the other channel, and these are the so-called bootstrap equations. The ones you worked in during the tutorial were not for D equals 4, they were for D equals 2. For D equals 2, the block is very similar. It doesn't have this factor. It has a plus sign here, and it doesn't have this shift by -2. So almost the same. For D equals 3, there's no closed expression for the block. So see, if d equals 4 and d equals 2, very similar. D equals 3, we could work out any term in the expansion we want. It's the same logic as yesterday. But no one knows of a clean, closed expression, how to resum it into something nice with hypergeometrics. It's what it is. But in practice, you can, if you want numerics, if you want to do it numerically, you can find good representations. But okay, for d equals 4, here it is. For d equals 2, it's what you used. Now, these equations, they are not easy to work with. It's not like you go look at these equations and find all possible CFTs. But there are things we can do, like what you did in the tutorial. So in the tutorial, you applied functionals to this equation. And if you apply some functional, you can sometimes prove that some things are impossible. Because you can show that some terms cannot add up to 0 if they are all positive, or if they are all on the same side of some planes, right? For example, you showed a stronger result, but this is a particular weaker statement of the result you proved. In 2 dimensions, there is no CFT where the lowest operator has dimension 1/8 and the next to lowest is somewhere above 1.5. This doesn't exist. Such CFT doesn't exist. You proved it yesterday, right? In the tutorial. Now, you also showed that you could also, instead of studying bounds on spectrum, you could put bounds on 3-point functions, right? So one result that you found, or that you understood that you could find in particular, is the following. Given a spectrum, a set of dimensions delta j, only delta j, let's say that I have with the lowest, let me call it delta, and say the next to lowest, let me call it delta prime. Then we could, using the bootstrap equations, we could show that, for example, the structure constant between the lightest of 2 lightest operators with the next to lightest, for example, that this needs to be bigger, or that this is bounded and needs to be smaller or equal than some number. And this number you could find through this bootstrap. So let's have in mind that the bootstrap gives us a way of making such statements, such powerful statements. Now we'll put this statement on hold and come back to it in a few classes. But for now, it's one piece of knowledge that we know. Now, I want to tell you how we would go about finding these blocks in a more clever way. I feel like it's a little bit sad that it would be a bit sad if I didn't tell you. So was this explained in the CFT lecture? How would we find the conformal blocks? No? Okay. So let's discuss a little bit of an alternative derivation of the blocks. And the basic idea is to think that the block is describing the propagation from these 2 points that you fuse into something else. And so we want to describe propagation across this sphere. And the idea is to think that to measure this propagation, what we will do is measure the quantum numbers of what is flowing. Remember that this is how you derive the form of a plane wave. You say the plane wave has definite momentum p, right? So what equation should a plane wave obey? Because it propagates momentum p. It should obey the equation that operator p times plane wave is equal to number p times plane wave. And then you get a differential equation, you solve, and you get the plane wave. What about a spherical harmonic? Spherical harmonic propagates things that have definite angular momentum. So what equation does it satisfy? Casimir of total angular momenta acting on conformal block equal jj plus 1 times conformal block. Solve that differential equation, you get the, I said conformal block, I meant spherical harmonic. Solve that differential equation, you get the spherical harmonic. So the idea is to try to think like that, but for the conformal group. Instead of being the translation operator, instead of being the total rotation operator, we need to do it for the full conformal group that has a bunch of other generators. Okay, so that's the idea. So we will construct the analog of the Casimir for the rotation group, which is just the conformal Casimir. Let me write it down and tell you what it is. So that object, that Casimir, is defined is the combination of generators that commutes with all other generators, like the total angular momentum. So it's a good way to measure quantum numbers. And it's given by the following generators of the conformal group. This one are the rotations. I take rotation squared. So this would be what we would write for the Casimir of the rotation part, if I only had the rotations. Right? So we didn't discuss much rotations because they are so trivial, right? But rotations are, you just flip x to, this is like x mu dx nu minus x nu dx mu, right? So some simple rotation generator that rotates the points. Another one that you have is the dilatation operator. So this would be just the dilatation operator. And then you have translations. They are also part of the conformal group. And special conformal transformation. So the only one that maybe deserves a few words is this one. These are special conformal transformations. And so let me first say that each of these generators is in one-to-one correspondence to a conformal transformation that we can make. Rotations are rotations, dilatations we saw already, translations we saw already, and then we are always using inversions. So inversions are a very discrete operation, right? You do it once, then you do it again, and you go back. It's a Z2 operation. So there's no infinitesimal version of an inversion. You either invert or you don't invert, right? That's different from all other transformations, right? A rotation, you can do a small rotation. Translation, you can do a small translation. Dilatation, you can make a dilation by something very close to 1. But inversion, no. So special conformal is a little bit like the infinitesimal version of that inversion. In fact, a special conformal transformation, K, is nothing but what you get if you do an inversion, then you translate, and then you do an inversion again. Okay? That can be infinitesimal, right? So you can invert. After you invert, you shift, and then you invert back. That's a small operation if the shift you do is very small. Right? If you don't do any shift at all, it's nothing, right? And so this is another generator. Now all these generators, they are in one-to-one correspondence with transformations. X goes to X tilde that preserve the metric in up to a wild transformation. And they, if I define this, if I compute their algebra between these generators, I can easily check that this guy commutes with all generators of the algebra. Right? So this object here is like the total angular momentum that it commutes with any generator. Like commutes with p mu, m mu nu. Well, I can write them all. K mu and d. Yeah.
If you wanted to derive the form of this, should you just go to like the SOD2 representation and then write the actual Casimir that we know how to write for SOPQ, and then would it be this?
Yes. You could do it like that. Or you could know it's a quadratic Casimir, you write anything that's quadratic and you fix the coefficients by imposing this equation. Okay, so, but anyway, this is a correct statement. And now, what do we know about this operator? We know that this operator, this Casimir operator, if you act on some operator, OK, that has dimension delta and spin s, that is, just measures these quantum numbers, and it gives us something, the analog of jj plus 1. It gives delta, delta minus 4, plus s, s plus 2, times the operator. Okay? So this is just the analog of just j plus 1 acting on an operator.
So this action is commutator, or what do we mean by the state of an operator? Something.
Yeah, so here I think I have a state that operator generated and I act directly. I think in terms of operator itself, it will be the commutator of this with the operator as usual. All right. So if I do, yeah. Okay.
We know the action of D and M on O, right? But how we understand the action of K on O? Like I think it's kind of definition how D and M acts on O, right? By delta and S.
Yeah.
The K part?
You also know how K acts on O. You get it by knowing how what transformation K generates on the coordinate. Right? In the same way that dilatation, for example, dilatation changes x tilde to lambda x, right? So it acts on O by the operator x dot dx, applies dilatation. You figure out how K acts on locations, and you convert that into a differential operator acting on O. Okay. But anyway, I want to give you a flavor of the derivation. Everything we are using here is just to give you an idea. How could we guess some kind of hypergeometrics like that? I'm not this is really a parenthesis, just because I feel bad that I gave you this formula without giving you an idea of how normal people could derive it in one day, instead of 1 year of work of trying to guess patterns in resumming things. Okay, so the idea will be that we will, knowing this, let me see, we will do the following. Right, so now let's consider the Casimir operator 1/2 of J acting on operator 3 plus J acting on operator 4 squared. Namely, what we are going to do is to act with the Casimir on these operators 3 and 4 only. All right, so we think of them as differential operators that we are going to act on points 3 and 4 only. And we are going to act with this differential operator acting on the conformal block, F, okay. Now let's see what we would get if we act on this. So now we will act on this conformal block because we want, and we will see that the action can give two different things. And from those two different things, we will learn we will get a differential equation from this conformal block.
Is there a difference between J plus J square or J square plus J square, or just a notation?
By J square, I just mean that each of these generators here, I replace them by, for example, D square. D would be D acting on 3 plus D acting on 4.
I see.
Right, so it's a dilatation that applies, you apply the symmetry to operators 2 and 3, but not to 1 and 2. 1 and 2 you don't touch. It's crucial. You see? Yeah, that's crucial. Okay, so now let's continue that equation. So that's equal to what? Remember, the blocks were the sum over n b mu1 up to mu n. That was a function of okay. Okay. I'll have to fix something there because in my notes I did something a bit different. A function of x3 minus x4, right? And then there was some derivative with respect to x3 mu1, derivative with respect to x3 mu(n), and then correlation function of the operator OK with the operator O1 and O2. Right? This was the way we did it, right? So then I want to act with the Casimir that acts on operator 1 and 2. Sorry about that. So let's consider here 1 and 2. And so what we want to do is act with that generator that acts on 1 and 2. You see that this is just stuff that depends on 3 and 4, so nothing depends on 1 and 2. And so what I'm doing is putting the generator here, right? So here we put J1 plus J2 squared. Now, these generators, we can replace this guy here by minus the generator acting on point K, since J1 plus dot 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 plus JK, J1 plus J2 plus JK, kills the 3-point function, because this the acting with all the generators would be doing nothing. If I have a 3-point function, if I rotate everyone, I'm doing nothing, right? And so I can trade action on these guys by action on JK. But the action on JK, then the action on JK, when I replace 1, 2 by K, will just give me the value of the Casimir there. So this will just give delta minus 4 plus spin plus 2 on the one hand. So on the one hand, we conclude that this object here just generates this number times the conformal block. On the other hand, this object, like we said, is a differential operator. Each of those operators is a differential operator. So on the other hand, this is equal to some differential operator acting on this function f, where this differential operator acts on points 1 and 2. Now, this is not yet perfect because this differential operator acts on points 1 and 2, but we remember that this f, we can make an ansatz for f. We know that f has this x1 minus x2 to the power 2 delta, x3 minus x4 to the power 2 delta, and then whatever is here must be just some function of cross ratios, z and z bar. And the goal is to find this function. So now we take this differential operator and we commute it through till it acts there. In other words, we make it pass by this prefactor, and by passing by this prefactor, it will be slightly different when it reaches this operator D. And in this way, we end up with the equation that a slightly different differential operator, let me put the hat, no, the hat is what I did already, okay. Let me make double line, something like this. A slightly different differential operator 1, 2, that will now be a differential operator that only acts as a differential operator in z and z bar, acting on the function f that I want to find, is equal to this Casimir times f. And there is a differential equation to solve. Okay? Now, if you do it carefully, let me write what this differential operator is. This differential operator, if you just commute through that, it's not complicated. I can write it down explicitly. It's something like this: z squared 1 minus z d2 dz2 minus z squared. You see, it's a second order differential operator, of course, right? By definition, plus and similar term for z bar. And then there is one more term, plus 2 z bar over z minus z bar, 1 minus z d dz minus z swap with z bar.
By d12 we mean this operator, j1 plus j2 whole square. No, not that. Means here, in this case, the top.
This. Sorry?
The d12 that we applied.
Right?
That operator is this j1 plus j2 or some other operator?
Yeah. This d operator is just this. It's just taking those where d is d1 plus d2, m is m1 plus m2, right?
Yeah.
So you just act with this differential operator, again, to be very explicit. So for example, d1, 2, now the straight d is just what? It's something like x1 dot d dx1 plus x2 dot d dx2, etc. So you just have some simple differential operators that act on locations. You commute them through, and they become differential operators acting on cross ratios. Much simpler, because before we had 4 vectors, now we have 2 numbers. Instead of a differential operator that acts on vector x1, vector x2, vector x3, we now end up with a differential operator that acts on 2 numbers, z and z bar. Much simpler. Still tough, but much simpler. And so now all you have to do is solve this differential equation. Early, this funny d acting on f equal that number times f, where this is the differential operator. Now, a differential equation is not enough, right? When you have a differential equation, what else do you need?
Initial or boundary condition.
Yeah, boundary conditions. So plus boundary conditions, and the boundary conditions, what could they be? What do we know easily about this block f? The way, which is related to the way we derived it, and not today.
You know how it behaves in the small z limit?
Yeah, exactly. The boundary conditions would be the operator product expansion. In other words, the small z and z bar, which you see is when points collide, 1 and 2 collide. So there we know how the block should behave. We can extract it just from the OPE, from what we did. We worked out the first term. We could work out 2 or 3 terms if we wanted. Then we would know for free the Taylor expansion of the block close to z equals z bar equals 0. And that would have to supplement this equation. Another comment is that this 2 here, this I did for 4 dimensions. This 2 is d minus 2. So if it was in d equals to 2, this term is not there. Then what you get a differential equation in z plus a differential equation in z bar. That's why in 2 dimensions, the blocks factorize. In 4 dimensions, if you write the differential equation pulling out this factor here, you kill the second term. And that's why after you pull it out, it factorizes. Function of z bar. In 3 dimensions, there's no trick like this. If you try to pull out some factor, you cannot do it. And that's why no one could find a closed form expression by solving those equations. So if you have a 2 there, you can use this trick. You put this, and after you put this, the differential equation will factorize. If you are in d equals 2, there's no such second line. Then you don't need to put this, and it's already factorized. In d equals 3, you have a factor 1 there, and with a 1, and no one can solve this equation. But you have the equations, you have the boundary conditions. You can compute them numerically, of course. And that's how, in modern terms, we would go about finding these conformal blocks. Okay. So this is more or less the end of CFTs for a while. We'll come back to CFTs probably next week, by middle of next week. But for now, for generalities about CFTs, we are good. We have everything we need for now. So now, let me recall a few things that we have played with. So far, but before I move on, so it's a very good point for if there is any question about the classes so far. Any confusion you would like me to clarify? Everything good? Am I going too slowly? Should I speed up or it's okay? Okay. So far, we encountered a couple of things. We encountered flat space. As far as geometry goes, that's what I want to say here. We encountered flat space. This was just this space-time. Dx square is dx mu, dx mu. We also encountered several times spheres. All right? Spheres are what? Are the points, the set of points y that are equally spaced something like this. And we also encountered another space, which were cylinders. Cylinders would have a space-time ds square, which would be something like some d tau square plus a sphere. So I would like to make a few comments about these spacetimes before moving on. So a few simple comments. So first of all, let me emphasize what we already did, that RD is not invariant under conformal transformation. Right? So on the contrary, when you do x goes to x tilde, dx tilde mu dx tilde mu is not equal, but instead there is this proportionality factor. Right? And we saw a couple of examples. For example, for an inversion, where x tilde is x over x squared, this omega factor is 1 over x squared. Okay. And in particular, for a finite special conformal transformation, which you, again, it's very trivial. You just do an inversion, then you shift, then you do an inversion again. X tilde, let me write how it will transform. X tilde would go to x. The vector x tilde would be equal to x plus some translation by b times x squared divided by 1 plus 2b dot x plus b squared x squared. This is a conformal transformation. And under this transformation, the metric ds squared goes to omega squared ds squared. The notation here, I hope, is clear. X squared means the norm of the vector square, right? X squared is vectors. Okay, so that's the first comment for the first bullet point. Now, let's continue making a few comments. Okay. Okay, so I want to make 2 more comments. The second comment I want to make, and we will go into more detail now, is that we have these spheres, right? But if we take spheres with a few sign flips, that is, we go to the equation for the sphere and we flip a few signs, then we'll start describing other symmetric spaces that are very similar but typically non-compact, and we get hyperboloids and so on. Right, a sphere has all signs plus. If I put some signs minus, then I get some hyperboloids or some parabolas. I start getting other non-compact shapes, but also very symmetric ones. We'll come back to this in a few seconds. The last comment I want to stress about this is that the cylinder has no interior. Don't be confused, right? That when we draw this picture, the cylinder, there is this, there is time, and there is the S, d minus 1. There's nothing inside, right? The cylinder is just the cover, right? Well, like S1 times R is just the outside, right? So it is just like that. Okay. So now let's make 3 related comments that are related to these 3 points. And now let me make 3 comments that are, these are all trivial comments. Now I'll make 3 comments that are a little bit non-trivial. And that will be novelty, I think, for you. Okay, so now we'll start with some new comments that are related to this. So let me use some open bullets to indicate it's a new comment. So the first new comment is the following. Consider the following metric, ds squared, which is not just dx mu, but you add an extra dimension. You consider dz squared, you add an extra dimension z. So you have x1, x2, x3, x4, and then you have z. And let's consider further that I divide this by z squared, and z is positive. Okay. So this, we would call this A, this metric A. So how would we visualize this metric? So you see that if I think of some direction z, at any fixed z, if I fix constant z, I get Rd. This is just Rd, right? So I get many copies of Rd. It's a stack of Rd, right? I have Rd at z, Rd at z prime, Rd at z prime prime, etc. Right? At each z, I have Rd. And as z increases, I get Rd multiplied by a rescaling factor that's going to 0. So it's like stacks of Rd that are becoming smaller and smaller. So a nice picture for it would be something like this is z. I think that this is Rd. And then I have a bunch of stacks of Rd that are becoming smaller as I go up in z. So at each fixed z, I get some Rd. It's like a stack of Rds. It's just a definition of a space-time. Okay, it's a definition. Now let's make a claim about this space-time. So a claim. A claim is that each conformal transformation x goes to x tilde can be promoted to an isometry of this space-time. So let's see what we mean. Oh. Okay, but maybe put an exclamation mark and let me stress another thing. So that is, in other words, the symmetry group of this space-time, that is the group of symmetries that leave the space-time invariant, is equal to the conformal group. Which is the group generated by the conformal transformation. So this is in striking contrast with what I said before. RD by itself is not invariant under conformal transformation. RD transforms. This one is invariant. So let's see how it works. Example. X tilde equal lambda x. This does not leave flat space invariant, right? This transforms flat space. How could I make this a symmetry? How can I transform Z such that this is really a symmetry of this spacetime? How could I change? I change X into lambda X. What should I change Z so that this metric is invariant? Lambda Z, right? If I rescale everything by lambda, lambda Z is a symmetry. Right? So X to lambda X was not, but if I compensate it by Z goes to lambda Z, now it's a symmetry. This one was a simple one, but now let me give you a complicated one. Example prime. X tilde going, let's write the conformal transformation that we like very much. X tilde goes to, or equal, sorry, X tilde equal, or X goes to, whatever, X tilde equal, or both. X goes to X tilde, which is equal to X plus B X squared divided by 1 plus 2 B dot X plus B squared X squared. If I close the parentheses after what I just started, this would be the usual conformal transformation. Right? Now the claim is that the following plus Z squared plus Z squared and Z tilde, and Z goes to Z tilde, which is Z over the same denominator, is an isometry. This, you see, would be the way that we would promote this transformation that would not be an isometry, it would transform. We have to deform it slightly. You see that if Z is very small, this is like the usual conformal transformation as we send Z to 0. So very close to Z equal to 0, to the first copy of RD, the transformation is just the usual conformal transformation. But as you move to the upper foliations, this transformation gets modified. Z also needs to be transformed a little bit. And in total, the two combined are now a symmetry of this space. They really leave the space invariant, right? ds squared goes to ds squared, not ds squared times omega squared. Note that related to this comment, Z equal to 0 is the boundary of this spacetime. So at the boundary of this spacetime, this first foliation here, that Z equals 0, I can transform points. I can map a point to another point, just in the same way as conformal transformations do, right? Like here or like there. But then that will be promoted to some non-trivial transformation acting on points everywhere that is Z-dependent as I go up. And it's completed into a full transformation of this space that leaves it invariant. It's just a true state. You will be asked to check this in the tutorial tomorrow. Just take the metric and check that this is true.
How do we, just because we define Z greater than 0, this becomes the boundary. But
Right, that's right.
it could be
Right now, z equal to 0 is just the way we defined it. It's also clear that z equal to 0, this explodes. So you could only go up to z equals 0. So from that point of view, z equal to 0 is the boundary. If I did not know, if I started at z positive, I would see that z equal to 0 is the maximum I can go. But the way I defined it, I made it manifest that that was the boundary. What was the question? Okay, so that's the first comment. Now, related, now let's make the counterpart of the second comment, this hyperboloids and so on. So the comment now is that the following metric that I'm going to write notice that it's like a sphere but with a few minus signs. And the claim is that this object is an hyperboloid. So let's see how this works. So first, let me make a comment that here we have d plus 2 y's, right? There are d plus 0 plus minus 1, so d plus 2 y's. But there is one condition on these y's. So there is one condition, which is the condition I wrote here, that the square of them is minus 1. So in total, this is a d plus 1 dimensional space. Like the space we studied before, it was also d plus 1 dimension. It had rd plus 1 extra dimension, right? It's like a sphere, right? It's 3x1 squared plus x2 squared plus x3 squared equal 1, and it's a ball. It's a 2-dimensional sphere. So let's plot it to just see that it's an hyperboloid. And by plotting, I have to choose which axis to plot. And I will plot the axis y minus 1, y 0, and then here I plot all other y's. So I'm plotting the magnitude of the other y's.
so the d plus 2-dimensional space is the flat space, or there is something else?
You can say it's flat space, yeah.
Just
So there are d plus 2-dimensional y's in some flat space that would be, it would have 2 negative signs and everyone else plus, so it would be like Minkowski 2 comma d. So a signature of minus, minus, plus, 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 plus. And then we put this constraint there. Now, let's see. So what equation do we get here? You see that this y1 squared minus this with minus minus, right? So please follow me so that you can see what I'm doing. So you take these guys and you put them on this side. You take this one and you put the one here. Now on the other side we get y0 squared plus y minus 1 squared. So that's a circle. And that circle is equal to what? It's equal to 1 plus something positive. So when this something positive is 0, we get a circle of unit radius. Here, right? So this is 1. And then as these guys increase, the circle just becomes bigger. So it's an hyperboloid like this. Right? Clear? It's just an hyperboloid like this. What would be the metric of this spacetime? The metric of this spacetime, we can call this metric B. This metric of ds squared would be just the flat metric, like what's your name? Manu said. dym, dyn, eta mn, just a flat metric where eta is this metric here, minus, minus, plus, 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 with the constraint that y squared equal minus 1. Like for a sphere, right? It's the flat metric with a constraint that the y squared set up to 1.
So one question means why is this means if it has just circular cross section doesn't mean it will become hyperboloid, right? A paraboloid will also have circular cross sections or something.
By is an hyperboloid, I mean this picture is correct.
Yeah, but that shape is a hyperbola is not clear, right? I don't know, means I don't see it.
Okay, I don't know, maybe there is a fancier definition that, but this shape you agree, right? There is a circle, and then the circle increases and so on. That's all we need. Now, what's the boundary of this spacetime? The boundary is more interesting in this case. You see, the boundary would be what? If this keeps going on forever, right? The boundary is where this point's asymptote, right? This point is not at a boundary, but it's very far away if this continues growing, etc., right? So eventually, if I take a family of points like this, like these points that are growing like this, they are going more and more towards the boundary. So where are they asymptoting towards? How could we think of where these points want to grow, want to go? And the answer is quite cute. You can think of light rays that pass by the origin. So let's draw a light ray that passes by the origin. It will do something like this. And so this hyperboloid asymptotes becomes arbitrarily close, closer and closer to the light ray. And so to each light ray, what's a light ray? A light ray is a set of points y that are identified. Y is the same as lambda y, right? Because it's a ray. And y square equal to 0. It's of light. Okay. And the boundary of this spacetime is the set of light rays. Right? To each light ray represents where each point approaches at that boundary. And so let me write it somewhere. This conformal block stuff we don't need anymore. Just move it up. And so the boundary equal to the set of light rays. Okay, this is a state. And that is an hyperbola. And now finally, let me make a comment, one last comment about cylinders. So let me construct a third metric, C, ds square, that will be like a cylinder, but with interior, minus cos square of rho dt square plus d rho square plus sinh square of rho times a d-dimensional sphere. Okay. So let's draw how we should think of this spacetime. The way we think about this spacetime is as a very big cylinder. You see that at each fixed rho, if I fix rho, we get a cylinder, right? If you fix rho, d rho is 0. This is a number, this is a number. And we get d tau square times a number, you don't care, right? You get time and the sphere. So for each fixed rho, it's a cylinder, right? So there is at the center, then there is a radial direction rho, and at each fixed rho, we get a cylinder. Okay. And so the picture is, there is this radial direction, that's rho, there is time, t, and there is the sphere, like before. So it's similar to before, but now there is the inside and the outside, there is everything. And now let's see what the boundary would be. So if we take rho to go to infinity, then this metric would become e to the 4 e to the 2 rho. There will be some divergence. Like there is a divergence in 1 over z squared over 4 times minus dt squared plus d square as d minus 1. And so asymptotically, as I'm going to rho towards infinity, I get precisely a cylinder like the one we saw before. well, it's not exactly like the one we saw before because here I have an honest time. If you want to do the one we saw before, you should do t goes to I tau. Then you flip this sign and it's exactly the one we saw so far. Right? This is really a sphere times time, honest time, not a cylinder. But okay, it's a cylinder. And so the boundary of this space-time is a cylinder. And this space-time is d plus 1 dimension. And so clearly, A, B, and C have something to do with CFTs, right? They all have some moral connection, at least have something to do with CFTs. I hope you agree with me. I hope you believe me that they all seem kind of morally or psychologically or, related to CFTs. And now let's make here a big claim. Is that these spacetimes A, B, and C defined basically are the same spacetime. And this is what is called the ADS spacetime, anti-de Sitter spacetime. And that will be the subject of tomorrow's tutorial, understanding how that goes, how is it, how could it be that the boundary of a space-time can be sometimes R, sometimes a cylinder, sometimes some light rays, how is it all consistent? How can I see it's really an equality? There is no wishy-washy, it's really they are equal. How are these metrics equal? How do I go from one to the other? How can we understand this? And that's something that it's a long tutorial. You'll probably not have time to finish it all during the tutorial, but do finish it at your own pace at home if you don't, because it's an important one. And I think this is a good point to stop today.